October 14th, 1943, Schweinfurt, Germany, 14:20 hours. The B-17F Flying Fortress shuddered as another flak burst erupted 50 yards off the starboard wing. Lieutenant James Harrington gripped the control column tighter, his knuckles white beneath his leather gloves. The temperature inside the cockpit read -40 degrees Fahrenheit, but sweat beaded on his forehead nonetheless. "Flak intensity increasing, skipper," the navigator called through the interphone. "Looks like we've got a wall of it ahead." The aircraft designated Lucky Lady was part of the 305th Bombardment Group, flying at 27,000 feet toward the ball-bearing factories that kept the German war machine rolling. Harrington squinted through the windscreen. The sky ahead had transformed into a deadly constellation, dozens of black puffs of 88mm flak shells, each one capable of tearing through aluminum skin and flesh with equal indifference. The formation tightened as they approached the target area. Staying in tight formation was essential. It concentrated the defensive firepower of their 50 caliber machine guns and ensured bombing accuracy, but it also made them perfect targets for the German anti-aircraft gunners below. Another explosion, this one closer. The Flying Fortress bucked violently. A jagged piece of shrapnel tore through the fuselage just behind Harrington's seat, with a sound like a hammer striking an anvil. The co-pilot flinched, but maintained his position on the controls. The bombardier's voice crackled over the intercom, strained but steady. 3 minutes to target. They were committed now. There would be no turning back, no evasive maneuvers. The mission parameters required a straight, level approach for the Norden bombsight to work properly. Harrington knew the statistics. On average, a B-17 could absorb 20 direct hits from 20mm shells before critical systems failed, but the 80mm flak bursts were another matter entirely. One well-placed hit could send 10 men plummeting to their deaths in seconds. And lately, the Germans had gotten very good at placing those hits. 8th Air Force Headquarters, High Wycombe, England, November 1943. The somber faces around the briefing table told the story before a word was spoken. Colonel Curtis Matthews studied the casualty reports with growing alarm. The October raids on Schweinfurt had been a disaster. 60 bombers lost, over 600 men killed, captured, or missing. The cold mathematics of strategic bombing was becoming unsustainable. The problem is penetration, Major Robert Thorne, an engineering officer, explained as he spread technical diagrams across the table. The German 88s are firing shells with proximity fuses. They don't need direct hits anymore. The flak bursts near our aircraft, and fragments tear through the aluminum skin like it's paper. The B-17G models were already incorporating lessons learned in combat. More machine guns, better armor plating around critical areas and crew positions. But each addition of armor meant less bomb capacity, shorter range, reduced performance. It was an engineer's nightmare, a zero-sum game with lives in the balance. Our crews report that the damage is concentrated in predictable zones, Thorne continued, pointing to shaded areas on a B-17 schematic. Engine nacelles, wing roots, bomb bay, and tail assembly take the worst hits. The Germans have studied our formations and know exactly where to aim. A week later, the losses continued. The 91st Bombardment Group returned from Bremen with 14 aircraft sporting flak damage so severe that 6 were deemed beyond economical repair. Maintenance crews worked around the clock, patching holes, replacing control cables, swapping out damaged components. Chief Master Sergeant Walter Kowalski had witnessed the carnage firsthand. After 27 years in the Army Air Forces, he had developed an intuitive understanding of aircraft vulnerabilities. Walking through the hangars at RAF Bassingbourn, he paused to run his fingers over the jagged holes in a B-17's fuselage. The aluminum skin, just 32 inches thick in many places, provided almost no protection against flak fragments traveling at supersonic speeds. "The flak doesn't have to destroy the aircraft," Kowalski explained to a group of newly arrived replacement pilots. "It just has to hit something vital: control cables, hydraulic lines, oxygen systems, fuel tanks. One small piece of metal in the wrong place, and 10 men die." The statistics confirmed his assessment. By late 1943, Flak was accounting for nearly 75% of all bomber losses over Germany. The Luftwaffe fighters remained deadly, but the integrated air defense system of radar-directed anti-aircraft guns had become the primary killer of American airmen. The fatal flaw was fundamental. Heavy bombers needed to fly straight, level, and in formation to deliver their payloads accurately. This predictability was what made them vulnerable. Evasive action during the bomb run was forbidden. It would scatter the bombs uselessly across the countryside rather than destroying the target. The doctrine of precision daylight bombing required this deadly compromise. RAF Thorpe Abbotts, England, December 1943. Captain Maurice Abrams had never intended to become a combat engineer. Before the war, he had been a professor of metallurgy at the Massachusetts Institute of Technology, specializing in aircraft alloys and stress analysis. His research on aluminum fatigue had earned him modest recognition in academic circles, but seemed destined for obscurity in the dusty pages of engineering journals. December in England brought perpetual dampness that seemed to seep into everything: hangars, barracks, and the bones of the men who fought the air war over Europe. Abrams pulled his coat tighter as he walked among the damaged B-17s that had returned from the previous day's mission to Bremen. The 100th Bombardment Group had earned the grim nickname the Bloody 100th due to its high casualty rate. Abrams had been attached to the group as a technical liaison, but increasingly found himself working alongside maintenance crews, trying to keep the battered bombers flying. "Captain, take a look at this," Staff Sergeant Dan Miller called from beneath the wing of a B-17 nicknamed Carolina Creeper. The aircraft had taken severe flak damage, but somehow limped home on 3 engines. Miller pointed to a peculiar pattern of holes in the wing's aluminum skin. Abrams knelt to examine the damage. 3 flak fragments had penetrated within inches of each other, but their paths through the aircraft told a curious story. The first had torn straight through critical control cables. The second, entering at a slightly different angle, had been deflected by an internal support strut, saving the aileron controls. The third had been diverted by an ammunition box, harmlessly embedding itself in a non-critical bulkhead. Same type of fragments, same general entry point, completely different outcomes, Abrams murmured. "It's all about the angle of entry and what they encounter first inside." That night, Abrams couldn't sleep. The image of those 3 flak holes kept returning to his mind. He pulled out his notebook and began sketching, calculating angles of penetration and energy dissipation rates of different materials. By morning, he had filled 27 pages with calculations and rough designs. His MIT training in materials science, combined with observations from dozens of damaged aircraft, had sparked something. Not a revolutionary new technology, but a deceptively simple concept based on naval armor principles. "The Germans have turned the sky into an ocean," he wrote, "and our bombers are sailing through a storm of metal. What if we applied battleship protection concepts to aircraft?" Warships had long used angled armor, not just to stop projectiles, but to control how they penetrated. The sloped armor of modern battleships was designed to deflect shells rather than absorb their full energy. Aircraft couldn't carry such heavy protection, but what if the same principles could be applied using lightweight materials? Abrams requested access to the maintenance records of every bomber in the group. For the next week, he methodically documented damage patterns, creating a 3-dimensional map of vulnerability. The results were illuminating. Certain areas of the aircraft were statistically more likely to receive critical hits, and those hits typically came from predictable directions. "It's not random," he explained to Colonel Hammond. the group commander. "The German gunners are trained to target specific areas of our formations, and the flak fragments follow predictable paths once they penetrate the aircraft skin." Hammond was skeptical but intrigued. "What are you proposing, Captain?" Abrams spread his diagrams across the commander's desk. "Not more armor, sir. Deflectors. Strategic internal modifications that redirect flak fragments away from critical components. It wouldn't make the bombers invulnerable, but it might give them a fighting chance to return home." Hammond studied the technical drawings. "How much weight would this add?" "Less than 50 pounds per aircraft," Abrams replied. "Negligible impact on performance or bomb load. And you can install these deflectors using existing materials." "Yes, sir. We can repurpose aluminum from salvaged aircraft." The maintenance crews could implement the modifications during regular service intervals. Hammond leaned back in his chair, weighing the proposal against the mounting losses. The 8th Air Force was hemorrhaging aircraft and crews at an unsustainable rate. Conventional solutions weren't working. "You have 2 weeks, Captain," Hammond said finally. "Modify 1 aircraft. If it survives its next 3 missions, we'll talk about expanding the program." Abrams saluted. "Thank you, sir." "Don't thank me yet," Hammond replied grimly. "If this fails, it's both our careers. If it succeeds, we may save some lives. Get to work." RAF Thorpe Abbotts, England, December 16th, 1943, 02:30 hours. The maintenance hangar was deserted except for the lone figure working by the dim light of a shielded lamp. Captain Abrams studied the damaged wing section with intense concentration. Sleep had eluded him for days as his idea took shape. Dangerous, unorthodox, perhaps even impossible. The piece of flak-damaged wingskin before him told a story. The metal had been punctured cleanly, the edges curled inward where the fragment had penetrated. But what caught Abrams' attention was not the hole itself, but the surrounding material. The aluminum had absorbed some of the impact energy, deforming slightly before yielding. "It's not about stopping the flak," he muttered to himself. "It's about managing how it penetrates." Abrams had spent 3 years before the war working at the Curtiss Wright Corporation, studying material fatigue and stress distribution. Now, those seemingly abstract engineering principles might save lives. He pulled a sheet of paper from his pocket, calculations and sketches he'd been refining for weeks. The solution was counterintuitive. Instead of adding more armor, which reduced performance, what if they modified the existing skin of the aircraft? His concept was based on naval armor principles, specifically the way battleship armor was designed not necessarily to stop shells, but to control how they penetrated. If the bomber's skin could be modified to direct flak fragments away from vital components, more aircraft might survive to drop their bombs and return home. Abrams worked through the night, cutting small sections of aluminum and forming them into angled baffles. By dawn, he had created a small-scale model demonstrating his concept. It wasn't additional armor. It was a system of strategically placed deflectors that could be retrofitted to existing aircraft without significantly increasing weight or affecting performance. The implementation began the next day. B-17F, Missouri Compromise, was selected as the test aircraft, a veteran bomber with 23 missions already recorded in its logbook. The maintenance crew, initially skeptical, gradually warmed to Abrams' ideas as he explained the engineering principles behind them. "Think of it like a series of angled plates," he told Technical Sergeant Roy Patterson, the crew chief. "We're not trying to stop the flak. That would require too much weight. We're just trying to control where it goes after it penetrates the skin." Working night and day, they installed the deflector system throughout the aircraft's most vulnerable areas. Thin aluminum sheets, salvaged from damaged aircraft, were cut, shaped, and mounted at precise angles. Each deflector was positioned to redirect flak fragments away from control cables, hydraulic lines, electrical systems, and crew positions. The work proceeded in secrecy. Unauthorized modifications to combat aircraft could result in severe reprimands or worse. If Abrams' design failed in combat, the consequences would be measured in human lives. 3 days before Christmas, the modified B-17 was ready. Colonel Hammond inspected the installation personally, running his hands along the precisely angled deflectors. "It doesn't look like much," he observed. "Neither does a parachute ripcord, sir," Abrams replied. But both might save lives. The true test would come in combat. Missouri Compromise was scheduled to participate in the next mission, a raid on German U-boat pens at Bremen. Abrams requested permission to fly with the crew as an observer. Hammond hesitated. "You're not combat crew, Captain. I need to document how the system performs, sir. If modifications are required, I can implement them immediately upon return." After a long pause, Hammond nodded. "A permission granted. But remember, Captain, 10 men's lives depend on your theory working." 11, sir," Abrams corrected quietly. "I'll be on board too." Bremen, Germany, January 5th, 1944, 13:55 hours. "Flak at 2 o'clock. Heavy concentration." The voice of the tail gunner was tense but controlled as the formation of B-17s from the 100th Bombardment Group entered German airspace. 3 aircraft had been specially modified with Captain Abrams' deflector system, installed during intense overnight work sessions by maintenance crews who had been sworn to secrecy. The lead aircraft, Missouri Compromise, piloted by Major William Donovan, was one of them. Abrams himself sat in the radio operator's position, clipboard in hand, documenting every flak burst and its effect on the aircraft. The modification consisted of angled aluminum baffles placed at strategic points throughout the aircraft's interior. These deflectors wouldn't stop flak fragments, but they would alter their trajectory, redirecting them away from control cables, hydraulic lines, and other critical systems. The baffles were positioned based on statistical analysis of previous damage patterns, focusing on the areas most likely to receive hits. The first test came sooner than expected. A flak burst erupted directly beneath the Missouri Compromise, sending several fragments tearing through the bomber's underbelly. Abrams felt the aircraft shudder, but noted that it maintained level flight. Through a small inspection port, he could see one of his deflectors had done its job. A jagged piece of steel had penetrated the skin, but had been redirected harmlessly into a non-critical area. "Bomb bay doors opening," the bombardier announced. This was the moment of greatest vulnerability. The aircraft was committed to a straight, level approach, making it a perfect target for the German gunners below. The flak intensified as they approached the target. Black puffs filled the sky around them, each one potentially fatal. The B-17 to their right took a direct hit to its number 3 engine. Flames erupted instantly, and the stricken aircraft fell away from the formation. Another violent impact rocked Missouri Compromise. A flak fragment had torn through the flight deck, missing the co-pilot by inches. But the critical control cables, now protected by Abrams' deflectors, remained intact. The aircraft continued its steady approach to the target. Bombs away. The B-17 lurched upward as its payload fell toward the industrial facilities below. Now came the turn away from the target. Another vulnerable moment as the formation banked, exposing different areas of the aircraft to the flak batteries. By the time they crossed back into Allied-controlled airspace, the formation had lost 4 aircraft, but all 3 of the modified B-17s had survived. Despite sustaining multiple hits, Missouri Compromise alone had taken 17 documented flak hits, any one of which might have been fatal without the deflector system. Upon landing at RAF Thorpe Abbotts, the ground crews were astonished by the pattern of damage. The flak had penetrated the aircraft's skin, but in almost every case, the fragments had been redirected away from critical systems. Control cables remained intact, hydraulic lines unscathed, crew positions protected. Colonel Hammond walked slowly around the battle-damaged bomber, examining each hole with growing amazement. "I've never seen anything like it," he admitted. "The hits are there, but none of them in lethal spots. It's as if the Flak knew where not to go." One test mission wasn't enough to prove the concept, however. Over the next 3 weeks, the 3 modified B-17s flew 12 more combat missions, accumulating a total of 94 documented Flak hits. None suffered mission-aborting damage to critical systems. The evidence was becoming impossible to ignore. During a period when the group lost 11 unmodified B-17s to Flak damage, the 3 test aircraft continued to return, mission after mission. Abrams continued to refine the system, analyzing damage patterns and adjusting deflector positions and angles for maximum protection. By early February, 10 more aircraft had been modified. The results were consistent. Modified bombers were surviving Flak encounters that would likely have destroyed unprotected aircraft. Word began to spread among the combat crews. A lucky modification was giving certain B-17s an edge against German Flak. 8th Air Force Headquarters, High Wycombe, England, March 1944. General Doolittle studied the statistical analysis with undisguised interest. The numbers were compelling. Over the past 8 weeks, 57 B-17s had been modified with the Abrams deflector system. Of those, 49 had survived direct Flak hits that would likely have been fatal to unmodified aircraft. The loss rate for modified aircraft is 14% lower than standard configuration bombers flying identical missions, Colonel Matthews explained. Maintenance reports show critical system damage is reduced by nearly 60% when the deflectors are installed. The system had undergone continuous refinement. Abrams and his growing team of engineers had analyzed damage patterns after each mission, adjusting the placement and angle of the deflectors to maximize protection. The modifications added only 47 pounds to each aircraft, a negligible weight penalty that didn't affect performance or bomb load. By April 1944, the system had been standardized and approved for fleet-wide implementation. Maintenance crews across England worked around the clock to modify every B-17 and B-24 in the 8th Air Force inventory. The technical drawings were sent back to Boeing and consolidated, where the deflector system was incorporated into the production line for new bombers. The timing proved crucial. As the air war intensified leading up to D-Day, the German Flak defenses grew even more formidable. The deflector system couldn't save every aircraft, nothing could, but it significantly improved survival rates during the critical bombing campaigns of 1944. Captain Abrams, now Major Abrams, was awarded the Legion of Merit for his innovation, but the true measure of his achievement was recorded in the mission statistics. The 8th Air Force's operational readiness rate improved by 23%. More aircraft returned from each mission. More aircrews completed their 25 mission tours and returned home. By the summer of 1944, the Germans had noticed the decreased effectiveness of their Flak batteries against American bombers. Captured intelligence documents revealed their puzzlement at the sudden change in vulnerability patterns. They responded by adjusting their fusing mechanisms and developing new types of Flak shells, but the effectiveness of Abrams' system persisted. The technical principles behind the deflector system influenced aircraft design long after the war ended. When engineers at Boeing developed the B-52 Stratofortress in the early 1950s, they incorporated evolved versions of Abrams' deflectors to protect against Soviet anti-aircraft fire. Modern combat aircraft still utilize the fundamental concept of controlled energy management that Abrams pioneered, redirecting rather than simply absorbing impact forces. In civilian aviation, the same principles found applications in crash safety design. Commercial aircraft fuselages were engineered to channel impact forces away from passengers during crash landings, saving countless lives over the decades. After the war, Abrams returned to MIT, where he established the Aircraft Survivability Research Center. His work on protective systems continued for another 3 decades, influencing helicopter design during the Vietnam War and eventually contributing to the stealth technology of modern aircraft. Yet few outside aviation engineering circles ever heard his name. The deflector system, like many wartime innovations, was classified for years after the conflict ended. By the time the details were declassified in the 1970s, new technologies had superseded Abrams' invention, and its significance faded from public memory. In 1985, at a reunion of the 100th Bombardment Group, an elderly Abrams met several of the airmen whose lives his system had saved. One former ball turret gunner, who had survived 42 combat missions in a modified B-17, embraced him with tears in his eyes. "We never knew who came up with that contraption," the veteran said, "but we knew something was keeping us alive when other planes weren't making it back. Thank you." Abrams died in 1992, his obituary noting his academic achievements, but making only brief mention of his wartime service. The true scope of his contribution, an estimated 427 heavy bombers and over 4,000 airmen saved, remained largely unknown to the general public. Decades later, fragments of the original deflectors would be displayed in the National Air and Space Museum alongside other innovations that changed the course of aerial warfare. But perhaps the most fitting testament to their value was written in a small notebook kept by a B-17 pilot who flew 35 missions over occupied Europe. "We took heavy flak over Merseburg today. 3 direct hits. Jenkins' aircraft to our right went down with all hands. Somehow, we made it home. The ground crew counted 27 holes in our ship. The old lady held together, despite everything the Germans threw at us. Another day we shouldn't have survived, but did." United States Strategic Bombing Survey, Final Report, 1945. Among technical innovations implemented during the air campaign, the Abrams deflector system is assessed to have significantly reduced aircraft losses due to anti-aircraft fire. The system represents a prime example of field expedient engineering under combat conditions and demonstrates the critical importance of adaptive technical responses to evolving enemy defensive capabilities.